Hello all. Today we're going to be discussing diodes, and I'm going to go ahead and get started on the material without wasting any time. Let me get started by drawing the symbol for a diode. It looks like this, like a little triangle, a line, and then your wire continues. And this side over here with the line is the negative side. And the other side is positive with the triangle over here. And the formal name for those are going to be the anode, which is positive, and then the cathode, which is negative. The reason why that's important here, for example, for a resistor, if you guys recall, you can attach a resistor to the circuit, and it doesn't really matter that much which side is which. You can attach it in any order. Because all it does is just resist the current. Doesn't really matter too much, but the special thing about a diode is it lets current in one direction. That is the whole purpose of it, in a way. So it has two modes of operation, right? So the first mode is on. When it lets the current through, it's on, and the formal name for this is going to be forward bias. And then the second mode is when it's off, which means it does not let any current through, and this is called reverse bias. And I'm going to go ahead and draw the little representation. So when the diode is on, it literally is basically like a regular wire. There's the positive, there's the negative. The current here is going to be greater than 0. The voltage is equal to 0. And the reason the current is flowing is because it's connected to another circuit. I understand if there's no potential difference, there would be no current, but we're just looking at the element itself. And then on the off situation, it's just going to be like an open circuit. So no current is going to flow. And that means I is equal to 0. And then the voltage is negative because the reason the current isn't flowing is because this side is actually going to be at a higher potential than this side, which is impossible because it only lets current in like that. So you might be wondering, how does that work, right? How would it only let current in one way? And you can actually test this, just by the way. Side note, if you have an LED, you can make a very simple circuit because LEDs are actually light emitting diodes. So you have your little LED, and if you want to attach it, you're going to realize you can only attach it with the correct polarity. It will not light up, and it's not broken. It's just that diodes do that. So how do they do that? That is where I'm actually just going to go through this briefly because our goal is to solve problems, right? Because this is a circuits, and we're not really going to be talking very, very much about the device physics, and it's not that important to be able to solve the circuit, but I will just discuss it real quick. So I'll do a little heading for us. So the way this works is the diode is made out of semiconductor material. There's two different types. The first one here is the p-type, and you can think positive for p-type. And the other type is the n-type, and you can think negative for n-type. And the p-type is semiconductor. Usually it's like silicon, Silicon Valley, ringing a bell for you, I hope. It is doped so that it's more positive, and it doesn't have more protons. That's not what's making it more positive. What makes it more positive is that it's missing some electrons, so it has something called holes. That's not too important, but I'll just mention that for you guys. And then the negative side has some electrons here, additional electrons, so it's negatively charged. And what occurs in the diode when it's in the on state, let me go ahead and draw that. So on. So the voltage up here on the anode is positive, and the voltage down here is negative. And so the holes, or we'll just think the positives right here in this semiconductor, they want to get away from this positive, right? And the negatives on this side want to go that way. So these electrons, the negatives are electrons, they're going to start flowing towards the plus, which means the current is going from the plus to the minus, just like I drew up here. This is the direction of the current. And the reason why we're saying the current is flowing that way is because current is the opposite of electron flow. So this is just our conventional current right there. Now, why wouldn't it... Oop, did a little too much backspacing, my bad. Now, why wouldn't it flow when it's off? And it's not actually off, and it's not actually, so up here, right, I drew it as a short, or an open, excuse me. This is a short. The reason, this is just a representation, but the diode is not a switch, so it's not actually open like that, but it's off because of what's happening to the electrons here. So I'll just go ahead and draw the diagram. So when it's off, the polarity, the voltage is negative. So that means it's flipped. So this side is more negative, this side is more positive. Now what happens here is the electrons on here, they are like perfect and they all bunch on this side. And then the holes, or the positives, all bunch on this side. So they're going away from each other. So which way does the current flow, right? It can't really flow. They're just moving away from each other, and there's just, you know, space here, I guess. Now, you might be thinking, well, here's positive and negatives next to each other. So why in the world wouldn't they just, you know, the positive go here, negative, and it's all bonded? Well, the reason why there is a little bit of that happening, and there's a region right here, it's called the depletion region. But I don't want to get into that too much because it's not that important for the class. But do understand it does some pairing. It's like the chemical that's inserted into the silicon that's doping it has a certain amount of valence electrons. So it's not like the other electron can just go into the valence that is already full of the element that only requires a certain amount of valence electrons. That would be kind of how I'd explain it. My apologies if that's a little far-fetched, but again, not super important. I'll go ahead and switch the color. And just for us to understand the whole, I know the voltage equals 0 or whatever, that might have been a little confusing. Let me just show you like the example circuit, right? Just super quick. So here's the diode. This side is plus, this side is minus. This is plus, this is minus. Right there. What's going to happen in the circuit? Current is going to go like that. Everything's looking dandy. And then if I flip it around, what's going to happen is no current is going to flow. So this is as if it were open. Not actually open. It's this situation right there. But hopefully that gives a little bit of a overview, I guess. Alright, so the last thing I wanted to discuss about the diode is the current and voltage relationship. So that IV curve, I'm going to go ahead and talk about this, and this will hopefully help us see why the element is called nonlinear, right? Because we've been saying, oh, nonlinear element in like the intro, but why? So here's a little blank graph for us, and let's kind of fill this in. So here's current, here's voltage. What do we know about the diode? Well, we know that whenever the voltage is negative here, the current will just be 0, right? Because of the whole electron scenario we just talked about. So this is reverse bias. And so that's off. I'll just put off for us to understand that better. And then whenever the voltage is positive, it lets the current through. So the current just goes completely through right there. So this is forward bias and on. Now, the problem with this graph here, this is the ideal diode. You can't just have infinite current going through, right? That would really make no sense. And so there's physical limitations and some other things that would prevent our IV curve from ever actually looking like that. So a more accurate representation of the IV curve here's I, here's V, is something like this. Maybe do a better one. Something like that. So we can see right here why it's nonlinear, right? If we think about the resistor is just a simple line. The relationship is V equals IR. R basically stays constant, and it's very easy to tell, you know, what the next value is. It's a simple element. Here, it's kind of hard to tell. If you had like some value here and here, or my bad, here, what's the value going to be right here? When it's a certain amount over, it's not going to be the same thing. It's kind of an exponential. So that really breaks apart. And the equation that actually governs the diode, I'll just go through that. It's I equals IS e to the VD n VT minus 1. And I is the current through the diode. IS is the saturation current. And then the voltage across the diode. And then VT is a constant. It is the thermal voltage constant. And that's going to be about 25 millivolts pretty much all the time. The N here is the ideality, I guess. It's like a number usually from 1 to 2. Depending on how like great your diode is, I guess. If it's a 1, it's basically perfect. And yeah, so this equation, right? We just kind of discussed all the components of it. It would be a little hard to solve. If you think about it, if you're going to try to do like KCL, KVL, whatever your circuit solving techniques, right? You try to plug this one in, yeah, it gets kind of messy fast. So there's actually two like better ways, I guess, instead of just trying to solve this fat equation every single time you are working on a circuit. There's two simple paths, so I'll go ahead and write. So one of the methods is the ideal approximation. And when we think about that graph we had up there for our diode, something like that, really, you can just approximate it as like that, right? And sure, it's going to be off for the values right here, but it'll still be okay. It'll still be doable, right? So you can do a little approximation, and this will be a voltage, maybe like 0.7 volts or millivolts. I don't know, some kind of voltage. And this is off. And then you can just say this is on, you know. And that's kind of good enough. Another way you could solve this is doing small signal analysis. So for AC voltages. So what you do here is that you have your graph. Let me just write that graph out so it'll be easier to tell. You have your diode equation. Now, if you recall back in like Calc 1, you guys learned about derivatives and, you know, approximating with a tangent. So you can really take a value here and approximate it with just a straight line. And what happens is when you zoom in on that right there, if you take like a very small value, if your input voltage varies from like this to this value right out here, that for that small area, that's why it's called small signal analysis, for that small area right there, you know, it's going to be pretty accurate. But I won't go into many more details about the small signal. I'll have a whole separate video about that. And in the next video, I will do actually examples. I'll just work through some diode problems, and hopefully that'll give you an even better understanding. But leave any comments with questions or if any of this was confusing. I know this was kind of quick, a lot of information, but I'm trying to do this as more of a supplemental video to maybe your lectures in class, or I can link to some materials in the description. I will actually have some videos that you can watch more about the device physics with nice animations from other channels that might give you some more insight. But for now, bye-bye.